In this mini lecture, I'm going to talk about arithmetic sequences. So the first thing is this word, arithmetic. The spelling of this word is exactly the same as the spelling of the word arithmetic. It's just arithmetic is a noun, whereas this arithmetic is describing a sequence, so that's an adjective. And there are other times where a word changes pronunciation depending on its part of speech. One favorite one I have is a very common English word that you pronounce differently when it's capitalized versus when it's written in all lowercase letters. And you may not be able to think of it, but it's an interesting word, right? Polish. And of course, if we write it all in lowercase letters, it's Polish. So English is a weird language. So arithmetic sequence. That's a sequence in which each term after the first term differs from the preceding term by a constant amount. The difference between consecutive terms is called the common difference of the sequence. This is a very common type of sequence. So this might be something like 1, 4, 7, 10, 13, and so on, where my common difference then is how we get from one term to the other, and in this case my common difference would be 3. We're going to usually use the letter D for the common difference. So for this sequence, if I just had 1, 4, 7, 10, 13, I'm adding 3 every time to get from one term to the next. So if I specify a first term a sub 1 and a common difference D, then that determines a unique arithmetic sequence. So that's all we need to know. And of course, the way it works then, to find the nth term, to find the current term, we take the preceding term and we add that common difference, right? To get the fifth term here of 13, we would take the fourth term of 10 and add 3. To get the fourth term, we take the third term and we add 3. That's what this recursion formula is saying to do. So example 1 here, let's just find these, the first 6 terms. Of course, to get each term, I just take the preceding term and I add D. So that would be negative 10 plus 4, which would be negative 6. And I don't really have to write this A2 plus D every time. So we know we're starting with negative 10. Then we get negative 6, then we get negative 2. Those are the first 3 terms. I just keep adding 4 every time, right? So I do plus 4, negative 2 plus 4 is 2. Then I do plus 4, 2 plus 4 is 6. And then I add one final 4, 6 plus 4 is 10. So those would be the first 6 terms of that sequence, right? Negative 10, negative 6, negative 2, positive 2, positive 6, positive 10. I can have a common difference that's negative. That's here in part 3. To get a sub 2 then, I get a sub 1 plus D. So that would be 12 plus negative 3, which would be 9. And then a sub 3 would be a sub 2 plus D. So that would be 9 plus negative 3, which would be 6. So I started with 12, then I have 9, then I have 6. And what I see that I'm doing here, I'm adding negative 3, which is the same thing as just subtracting 3. So I'm going to subtract 3 a couple more times here. So subtract 3 and get 0, subtract 3 and get negative 3. And so those would be my first 6 terms, 12, 9, 6, 3, 0, and negative 3. Now, if you're trying to find this, I didn't want to do that. If you're trying to find this common difference, D, and you know the terms of the sequence, we can always find D by subtracting the previous term from any other term. So, like, if I want my common difference here, if I've got 6, I just subtract 2 from it. So I pick a term and then the previous term and subtract. 6 minus 2 is this 4. 10 minus 6 is 4. Or here, 3 minus 6 is negative 3. Negative 3 minus 0 is negative 3. And of course, any pair of terms will work, but we could always just subtract the first term from the second term. So if you're finding this common difference d, you can always just take a2 minus a1. So up here, negative 6 minus negative 10. That would be negative 6 plus 10, which would be 4. That's equal to my common difference d. Or here, 9 minus 12 is negative 3, which is my common difference 3. So this d we can always find by just taking the second term minus the first term if we want. So that was a recursion formula. Let's see if we can figure out another way of coming up with a formula that's more of a general term and not a recursion formula. So a sub 1, of course, is just a sub 1. To get a sub 2, I take that a sub 1 and I add on that common difference d. To get a sub 3, then I take a sub 2 and I add on d. But what's a sub 2? Oops. Yeah, let's just get rid of that. Okay, a sub 2 is just a sub 1 plus d. A sub 3 is a sub 2 plus d. But a sub 2 is this a sub 1 plus d. So instead of a sub 2, I write a sub 1 plus d, and this plus d here just stays the same. But then I got a sub 1, and I've got plus d, that's plus 2d. The same thing works here then. I've got a sub 3, but a sub 3 is this a sub 2 plus d. And, wait, no. A sub 3 is this a sub 1 plus 2d. So that's what I put here. And then this plus d just comes along for the ride. Right? So a sub 4 is a sub 3 plus d. A sub 3 I found here is this a sub 1 plus 2d. So that just gets substituted for the a sub 3. The d goes along for the ride, but now I've got 3d. And of course that same thing continues. So a sub 4 is a sub 1 plus 3d. A sub 5 is a sub 1 plus 4d. A sub 6, a sub 1 plus 5d. Well, that sort of makes sense, right? I mean, if I've got a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, a sub 6, every time I have to add a d to get from one term to the next, right? A sub 1 plus d is a sub 2, a sub 2 plus d is a sub 3, a sub 3 plus d is a sub 4. So if I want to get to a sub 4, I had to add on 3 d's. If I want to get to a sub 6, I had to add on 5 d's to get from a sub 1 to a sub 6, right? If you compare this coefficient of d then to the subscript, to what term I'm on, notice it's always one less, right? So a sub 3, I've got 2d. A sub 6, I have 5d. And so in general, if I want a sub n, I have to subtract 1 and get n minus 1 times d. So this is a very useful formula, the general term of an arithmetic sequence with first term a sub 1 and a common difference of d. So if you want the nth term, you need n minus 1 d's. So if I want here the 8th term of the arithmetic sequence with first term negative 3 and common difference 5, we could write out all 8 terms, but what we can say is I know that a sub n is a sub 1 plus n minus 1 times d. And I want to find the 8th term, so I'm going to let n equal 8. So I know what a sub 1 is. A sub 1, the first term is negative 3. The common difference is 5. So a sub 8 here is going to be negative 3 plus 35. So the 8th term is going to be 32. On this one, if I wanted to check it, I could. My first term is negative 3, and then I just add 5. Negative 3 plus 5 is 2. 2 plus 5 is 7. 7 plus 5 is 12. 17, 22, 27, 32. So I could write out all 8 terms here, just adding 5 every time, and I see that that 32 that I predicted is the 8th term. Now, although that would have worked here in part A, I don't think we'd want to do it in part B. We want the 43rd term, okay? So I'm not going to want to write out 43 terms. I have better things to do, especially when I have this formula that's going to work. If I want the 43rd term, I'm just going to plug 43 in for n. And get d there. So now I know the 43rd term. Well, it says the first term is 100. The common difference is negative 12. So I'm going to have to multiply, let's see, 420, 432, 444. I better check that. I don't have a calculator here. 42 times 12. Let's see, 4, 8, 2, 4. Oh, good thing I'm checking. 504. Oh, we have 40 times 12, 480, and then 24 more, right? So 504. Oop. Just minus 504. So my 43rd term will be negative 404. Okay. So 420 and 84. That's what. Okay. So those aren't too bad. That's how we can use that formula. Now, one other thing we often want to be able to talk about, the sum of the first n terms. So if I have 8 terms like this and I want to add up all 8 terms, of course I could do it one by one, but it turns out there's a shortcut that we can use. So the way we develop this is a little tricky. So we're going to talk about this capital S sub n, and that's going to mean the sum of the first n terms. This is that summation notation that we talked about in the last section, in section 8.1. So that just says, remember, I is my index. We start with I equal to 1. We end at n. So I becomes 1, 2, 3, 4, 5, all the way up to n, and then we add them up. That's what this sum is. So this is my sum S sub n. We're going to write it forwards and backwards. So the first term, a sub 1. Second term, a sub 2, remember it's just a sub 1 plus d. And then the third term, a sub 1 plus 2d, right? We just add a term every time. The key is, what if I started with the last term? How do I get from the last term to the preceding term? Well, to get to the next term, I add d. To get to the preceding term, then I would subtract d. And so we write that up, and they would correspond in this way, right? I've got n terms. So here I start with 1 and I end with n. Here I start with n and I end with 1. Here I'm adding d every time to get bigger terms. Here I'm subtracting d every time to get smaller terms. But when I add up every pair just then, the d's end up canceling out. So I get a sub 1 plus a sub n. A sub 1 plus a sub n, the d's cancel. A sub 1 plus a sub n, the d's cancel. A sub 1 plus a sub n. So I've got 2 times the sum. How many of these are there? Well, there were n terms to begin with, so I get n pairs. So it's n times this sum. And so to find s sub n, then I just divide by 2. And you can actually think of the formula any one of these 3 ways. These are all equivalent for the sum of the first n terms. I usually think of either this middle one or this last one. So we either take the first plus the last and we multiply by n over 2, or I take the average of the first and the last terms, a plus 1 plus a sub n over 2, right? The average of 2 numbers, I add them together and divide by 2. I find the average term and I multiply by the number of terms. That really makes sense if you think about it. Let's see. Let's go to the next page. Now, there's a legend that the mathematician Gauss was asked to add up all these numbers from 1 to 100 when he was in early elementary school. So the teacher sort of thought that would keep these kids busy, especially at that time. They didn't have paper. They would do this like on a little slate, like a little piece of chalkboard. So to add up from 1 to 100, 1 plus 2 is 3. 1 plus 2 plus 3 plus 4. And so on, we get 3 plus 3 is 6 plus 4 is 10, but soon the numbers are going to get big and you're going to have to start adding them up one by one to keep track of the overall sum. But this mathematician Gauss sort of figured out when he was early elementary school that eventually, of course, you'd get to 50 and then 51, and then you could keep adding, and then eventually you'd get to 97, 98, 99, and 100. But what he realized then is that you could actually take the 1 and pair it with the 100, the 2 pair it with the 99, the 3 with the 98, the 4 with the 97, and the 50 with the 51. And of course, every one of those pairs adds up to 101. And how many pairs are there? Well, each pair has a lower number and an upper number. How many lower numbers are there? Well, from 1 to 50. And then we have the upper numbers from 51 to 100. So there are 50 pairs that add up to 101. So 50 times 101, well, 50 times 100 is 5,000. 50 more would be 5,050. Okay. The other way we could do this, to think of this as an arithmetic sequence, what I've got here is my first term is 1, and my common difference is 1. And I want to know the sum of the first 100 terms. So my S sub n, I can think of as n over 2 times a sub 1 plus a sub n. So S of 100 would be 100 over 2. The first term is 1, the last term is 100. So that's 50 times 101, which is exactly what we did there. Now, Gauss didn't necessarily know this formula, but he was able to use that pattern. So, sort of cool stuff there. A little historical background for this. What did I do? Went to those other lecture notes. There we go. So here we are back. So this example then, find the sum of the first 100 terms of this sequence. Now, the problem is here when we did the 100 terms, and I used this formula, I knew what a sub n was. I mean, for this problem, the sum of the first 100 terms is going to be s sub 100. So I'm going to need to use s sub n, which is going to be n over 2 times a sub 1 plus a sub n. So s sub 100 is going to be 100 over 2 times a sub 1 plus a sub 100. So 50, a sub 1, the first term, is negative 12. But I don't know what the 100th term is, right? Up here, I knew what the last term was. Here, I don't know what the 100th term in the sequence is, but I have a formula for a sub n. A sub n is a sub 1 plus n minus 1 times d. So if I want the 100th term, that's just going to be a sub 1 plus 99d. My a sub 1 is negative 12. My common difference here, well, d would be one term minus the preceding term, so maybe 2 minus negative 5. My common difference is 7, right? I'm adding 7 to get from one term to the next. So d here is 7. Oh. So 100 times 7 would be 700. So 7 less, this must be 693. And so this must be what? 681 must be my 100th term. All right? Yeah, 693. That works. So what do I get here? My sum then, I figured out that this number must be 681. So the sum of the first 100 terms is going to be 50 times 669, right? So 669 times 50 we get 33,450. What's really sort of cool about that is we've added up those 100 terms and we really don't even know what those 100 terms are. But we know if I wrote them all down, that's what it would add up to. That's really pretty amazing. I mean, that's a pretty cool thing. Okay, so example 4 now, evaluate this sum. Now, here we've got summation notation. So the sum as I goes from 1 to 50 of 3i minus 2. It's not even obvious at all that this is an arithmetic sequence. So we might just have to start by plugging in these values for I and seeing what we get. So I plug in I equals 1. So I get 3 times 1 minus 2. And then 3 times 2 minus 2. And then 3 times 3 minus 2. And then 3 times 4 minus 2, and so on until I get to 3 times 50. Oops. Minus 2. So what's that going to be? 3 times 1, I get 3 minus 2. 3 times 2, 6 minus 2, 3 times 3, 9 minus 2, 3 times 4, 12 minus 2, until I get to the last term, 150 minus 2. So I get 1 plus 4 plus 7 plus 10, and so on until I get to 148. So if I want S sub n, that's going to be n over 2 times a sub 1 plus a sub n. The other thing here is it doesn't tell me what n is, but I'm adding this as I goes from 1 to 50. So this is my first term, this is my second term, this is my third term, this is my fourth term. That's what I got when I plugged in 1, 2, 3, and 4. So this, I've got this is a sub 1, a sub 2, a sub 3, a sub 4. This is actually my 50th term. So I want my sum of the first 50 terms. That's what this summation notation has us do. It has us go from 1 to 50. So it's going to be 50 over 2. A sub 1 is 1, a sub n is 148. So it's going to be 25 times 149. I need a calculator. So 5, 4, 20 plus 4, 24. 5 plus 2 is 7. Now put in a 0. 2 times 9 is 18. 8 plus 1 is 9. I get a 2, 5, 12, 17, 37.25 would be that sum. So finally, here, example 5. Company A pays $24,000 yearly to start with raises of $1,600 per year. Company B, you start out making more, $28,000 a year, but you only get raises of $1,000 per year. So how much will each company pay in year 10? How much total money would a person earn at each company if he or she works there for 10 years? I've done this problem before, and it's sort of cool. I don't know if I have room to do the whole problem here. So for part A, of course, company A, my A sub 1 is 24,000, and my common difference, it's going up 1,600 every year. So my A sub n is A sub 1 plus n minus 1 times d. So in the 10th year, A sub 1 is 24,000. 10 minus 1 is 9. So that's going to be 24,000 plus 14,400. So that's going to be $38,400 you'll be making in the 10th year. For company B, well, its first term is 28,000, but its common difference is only 1,000. So I can talk about B sub n instead of A sub n. And so my B sub 10, the 10th year, B sub 1 is 28,000. 10 minus 1 is 9. So this would be 28,000 plus 9,000 would be 37,000. So, company A, you started out making less, 24,000 a year. Company B, you started out making more, 28,000 a year. However, by the 10th year, you're making more per year at company A than company B. This really isn't the best way to look at it, though. Over the long term, you want to look at the total you've made. So you would want to know what's the sum for the first 10 years. A sub 1 is 24,000. A sub 10 is 38,400. And for here, A sub 1 is 28,000 and A sub 10 is 37,000. So you'd want to compare those two numbers. It turns out that you're still going to make more total money at company B over the first 10 years than company A. Yes, you're better off in year 10 at company A, but overall, if you calculate these, use a calculator to come up with these results, you'll figure out that you're making more overall at company B. So that's an example of how these arithmetic sequences could help solve some real-world problems.